Let's start. Okay, so our next speaker is Fedya Manin, and he will talk about elliptic and quasi-regularly elliptic manifolds. So please.
Yeah, thank you very much for the invitation. It's really, a great honor to have Dylan as my warm-up act. Um, I'm going to talk about two different concepts that may or may not be related. And so I want to start by trying to justify these concepts. Why should we think about them from the points of view that they were originally defined from? And so these are both related to types of maps, which are particularly nice. And so I want to start with just some examples of, if we want to find particularly nice maps, what should those be? So for example, what's the nicest map um, from R2 to the torus? I think everyone will agree that this is the covering map. Um, but slightly harder, uh, what's the nicest map from R2 to the 2 sphere? And one could make the case that this is stereographic projection. But from my point of view, there's another candidate that the problem with stereographic projection is that it's sort of non-uniform, right? The derivative gets smaller and smaller as you get out. And so that makes it very unlike this covering map. And I want something that looks more like a covering map. And so one candidate would be you take the R2 and partition it into a grid and color it like a checkerboard. And then the black checkers go to the top hemisphere of the sphere, and the white checkers go to the bottom hemisphere, and then the vertices of this graph of this tiling go to some 4 points along the equator, let's say equally spaced, right? And the nice thing about this map is that it's a branched covering. So, um, except at these vertices, it looks like a cover. And at those vertices, it has degree 2. At lattice points, I guess. Right. And so I can say a lot of things about why this is a nice map, but there's sort of two main perspectives on this. And I'll start with the perspective that's maybe a little bit more alien to this audience, which is the metric geometry perspective. Um, right, so from the perspective of thinking about distances, right, what's good about this map? Um, it's one Lipschitz, right? Well, okay, so if I want to make it one Lipschitz, then I need um, these um, squares to have a side length pi, but that's not a problem. I can arrange that. Um, and the other thing that's nice about it is that it wraps efficiently um, around the sphere. So what do I mean by this? For any ball, let's say an R ball, right? The um, integral over that ball of the uh, pullback of the volume form on S2. so let's say this map is F, I guess, is at least some constant. It's proportional to the volume of the ball, right? So in other words, it's at least a constant times r squared. So in that sense, in this sort of a, zoomed out sense, it looks like a covering map. And actually, to make this into a definition, I want to slightly relax this condition. So I'm going to say that a map from Rn to a Riemannian n-manifold is a wrapping map if it's, I could just say Lipschitz, or I could say one Lipschitz, right? It sort of doesn't matter what version of the definition I take. But then the other piece is that as I take bigger and bigger balls, it might not be the case that every ball has sort of wraps efficiently around M, but at least some sequence of them do, right? So the lim sup of these integrals over over the volume of the ball is positive, right? So this condition Gromov called positive asymptotic degree, and I'm just going to say wrapping map to be a little briefer. And let's say that the manifold M is elliptic if it admits such a map. And so you can ask, which manifolds are elliptic? So we saw so far that tori and spheres are elliptic. And I'm going to give a lot more examples, but I'm going to delay that until I've introduced the other perspective on my initial example, this example, which maybe people here are more familiar with. So this is the analyst's perspective. So, right, start with the notion of a conformal map that preserves angles. And a quasi-conformal map, preserves angles up to a constant. So map distorts angles by a bounded amount. But we really want to imitate holomorphic maps, which are conformal except where their derivative is 0. Right, and if we take this condition, conformal except where the derivative is 0, in higher than one complex dimension, then it turns out it becomes extremely restrictive. And so it's a matter of interest to try to relax this condition a little and see what you get. And so this is, as far as I understand, the motivation for defining quasi-regular maps. So a quasi-regular map is uh, is quasi-conformal, except when its derivative is identically zero, roughly speaking. And if you want a non-smooth definition, then it satisfies this this condition. I guess I'm still writing it sort of, yeah. I guess this is a slightly more concise way of writing this condition. And so again, you can ask which manifolds admit quasi-regular maps from Rn, I guess, again, which n-manifolds. And in analogy with Gromov's definition, I think this terminology is due to Bonk and Heinonen. They called such manifolds quasi-regularly elliptic. Okay, so let me give some examples to sort of whet your appetite for general theorems about these things, because I think, at least for me, a big motivation of studying these two notions is that there's really a variety of phenomena that occur. So let me first give you some examples of manifolds that are elliptic and manifolds that are not elliptic. So we already saw tori and spheres. How about if you take CP2, or I guess CPN in general, but you can also take CP2, connect some CP2, and you can connect some another CP2 and maybe CP2 bar if you like. But what you can't do is connect some 4 CP2s. Another thing you can't do is take the Heisenberg manifold, so the real Heisenberg group mod the integer Heisenberg group cross, let's say, S500. This is not going to be elliptic. Here's another example of an elliptic manifold. If I take a bunch of Sn cross Sns and connect some them together, this is elliptic for R at most, I think it's 2n choose n over 2. And not elliptic higher than that. And let me give another slightly exotic example. I can take a 9-manifold, which I won't define exactly, such that the the real cohomology ring of this manifold embeds into the real cohomology ring of um, the 9 torus, but the rational cohomology ring does not embed into um, the rational cohomology ring of the torus. So what does this tell us? This tells us that right, the easiest way to imagine these wrapping maps is that you map to the torus, or sorry, that you go from Rn down to the torus, and then you take, some map of positive degree. And what this is saying is that there's really no map of positive degree from the torus to my M, but nevertheless, it is elliptic. So it has some kind of map like this, but that map is somehow, it has to be aperiodic. And this is an example where I guess these two examples, we don't know whether they're quasi-regularly elliptic, but the rest of these we do. So this, gives you some idea that maybe there's some relationship between these two, because these two we also know are not QR elliptic.
Are you sure about CPN? Because actually in my paper with you, we claimed this. And at the time we thought we had a proof, but I'm not so sure anymore. I could.
Oh, I don't know. I don't know that. Yeah. Okay.
I don't actually know whether CPN is QR elliptic. I mean, we claimed it in our paper, but I'm not so sure anymore.
Okay. Yeah. So you're in good company. There's another example like this, which is if you take an n torus and you connect sum it with a rational homology sphere, which maybe has ZP homology in some degree, between 2 and n-1. This is known not to be elliptic by a theorem of Gromov, and there's a paper of Luisto and Panka where they give a proof of the same theorem for quasi-regular ellipticity, but a few days ago, Pekka emailed me and said, wait, no, I think this paper is wrong. And we haven't yet been able to fix it, but there's hope. Okay, so let me, this is maybe enough examples. Let me give the theorems that these are examples of. So these are all closed manifolds, so let's explicitly make M a closed manifold. And let me make another table. So here I'm going to talk about elliptic manifolds, and here I'm going to talk about QR elliptic manifolds. And the reason it's good to care about closed manifolds is that these are both topological invariants. So ellipticity is even a homotopy invariant. And this is not hard to see. Basically, you can take any homotopy equivalence and between two Riemannian manifolds and make it Lipschitz. This is not a problem. And similarly, QR ellipticity, well, we know it's PL homeomorphism invariant. So again, if you have a PL homeomorphism, you can make it quasi-regular. But then, right, that generates a new open question, right? Are exotic spheres quasi-regularly elliptic? We don't know. Okay, what else do we know about these spaces? It turns out, are a bunch of topological obstructions to being both elliptic and quasi-regularly elliptic. So maybe I'll even erase this middle bar of this table because the next few entries are going to be the same. So for example, pi 1 of m always has growth type at most r to the n. So this is due to Gromov for elliptic manifolds and due to Varopoulos for quasi-regularly elliptic. And then the other big thing that we know is that there's an injective ring homomorphism from, this is what I wrote above, from the real cohomology of M to that of the torus, or if you like, the exterior algebra of Rn. So in the quasi-regular case, this follows work of Bonk and Heinonen and of Prywes, but this particular fact is due to Heikkilä and Pankka. And then in the elliptic case, it's a theorem of mine with Sasha Berdnikov and Larry Guth.
Is this rather recent? I mean, the left-hand side. I mean, the Heikkilä result is from this summer. What about the other, your result?
We put it on the archive in 22, so it's about a year older. Right. Actually, right, the story this is how I ended up collaborating with Eden, is that someone I was giving a talk about this, and someone came up to me afterwards and said, "Oh, this looks really similar to what Eden was doing," and so I got in touch with Eden, and we started working on proving the same theorem that Heikkilä and Pankka were already working on. And so, luckily, since this is a big part of Heikkilä's thesis, they beat us. Yeah, so this is 22 and this is 23. Right, and then there's this other result that I just mentioned that, oh yeah, and then a corollary of these two facts. So it just follows formally, and so it's true for both elliptic and QR elliptic things. And this is something that I noticed with Eden, is that the fundamental group turns out to be virtually abelian. Yeah, and then there's this other result that sort of doesn't fit into this story very well, which is that And I guess at this point, we only know it in the elliptic case. Um, if your fundamental group is the biggest it can be, which is virtually um, Zn, right, then this manifold is actually aspherical, and therefore um, it's finitely covered by a torus. Um, and hopefully this is also still true on this side. Um, okay, so we see that a lot of things are true for both of these concepts, and so um, a, a natural question which Gromov asked before knowing a lot of this is um, are these two properties actually equivalent?
Well, when did Gromov ask this? Because Gromov doesn't know what a quasi-regular map is. So.
In his book on metric structures.
Oh, yeah, but he has some other wrong definition of quasi-regular.
Oh, really? I mean, okay.
I think he calls, he for quasi-regular, he somehow assumes a priori that the map is Lipschitz, if I remember it right. So it's a bit.
No,
Oh,
if you actually read what he says, it seems like he speculates that it might be Lipschitz, but then he shows that it's Holder.
yeah, maybe I misremember, but maybe
But yeah, yeah, Gromov's book is not the most rigorous thing in the world, obviously. Um, but yeah, he did ask this question. And maybe the evidence for this is that um, the not only the obstructions are similar, but the proofs of the obstructions are similar.
Yeah, I was just going to ask about it. I mean, of course, I know the QR version of these results pretty well, and I have a good idea what the proofs are. But how do you prove this with your definition of ellipticity?
Yeah, so actually let me give that proof because it's not a hard proof. Um, so um, let me call this condition star. So here's the proof that elliptic manifolds satisfy this. So let's take generators for the cohomology ring. And I'm going to write AI for the degree of this WI. And I'm going to take representatives WI of omega I of the WI. So this is an AI form. And then take polynomials that give enough relations to give for this cohomology ring. So, or I guess, okay, this is not a polynomial ring, right? This is like um, a graded commutative free algebra. Um, right, but basically we want um, the the cohomology ring to be the free algebra divided out by the ideal generated by this set of polynomials. And then, right, for each of these polynomials, if we plug in these forms, then we get something that's cohomologically trivial, so it's an exact form. So it's D of something, and I'm going to call that alpha J, right? And this alpha J lies in, this is a Bj minus 1 form, right? Bj is the degree of the polynomial. So then suppose we had a wrapping map of our manifold, and what we're going to do is take these forms and pull them back and rescale them. So for every t, we can define ft of x to be f of t of x, right? So this is t Lipschitz. And we take rescaled forms so that, right, we're rescaling them in such a way that they still satisfy all these relations. So this is so that d alpha jt is still pj of the omega its. But then, right, the way we rescaled this, the operator norms of the omega its are at most 1, but since the alpha jt's are degree bj minus 1, but we divide them by t to the bj, their operator norms are actually going to be 1 over t.
Sorry, what do you mean by operated on?
I just mean if you plug in an orthonormal frame, right? This is the largest it can get. I guess, you know, the one here, yeah, I should not use, right? This is times some constant. Right, and now the fact that the map has positive asymptotic degree, right? This means that there's a sequence of t going to infinity such that if we take this integral, this is at least some epsilon. And now we can apply Art's law Ascoli, and we get a subsequence, let's say tk, going to infinity, such that right, there's a limit of all these forms in, so where does this limit live? It's an L infinity limit, and, and it lives in flat differential forms. Um, so this is roughly forms that are L infinity with L infinity differential. And since these are all closed forms, the L infinity differential comes for free in our case. Um, and then the the limit of the alpha j tks, right? This is just going to be zero. And this notion of flat convergence um, it commutes with everything you want it to commute with. So um, with a differential, the wedge product, and of course, since it's a weak limit with integration by definition. And so this actually gives a homomorphism from um, from the cohomology ring of M to flat forms on Rn. Um, and moreover, right, such that the integral over the one ball of the, uh, whatever polynomial you need to take to get the fundamental class, um, this is going to be at least epsilon. And right, so in particular, this fundamental class, right, this is um, is non-zero on a set of finite measure. Sorry, on a set of positive measure. And so, right, these flat forms are only defined up to a set of measure zero, but this means that we can evaluate at some point to get a homomorphism from this cohomology ring to um, to the exterior algebra where the image of the fundamental class is non-zero and therefore it's injective. So I guess for those who are not as familiar with the story for quasi-regular maps, let me just briefly explain what you need to do to modify this proof to work for quasi-regular maps. So you still take forms on some balls. Right, but maybe these balls are not around zero. Um, and you still do some kind of rescaling. But maybe the factor is no longer going to be the radius. And then you still take a limit, but It's no longer an L infinity limit, it's an LP limit for some finite P. And that forces you to do somewhat more work. So, the same, essentially the same steps still work, but each of them is much more work.
Yeah, I mean,
Um,
in your case for elliptic, right? I mean, you have Arcela Ascoli, which somehow makes it kind of easy to extract some convergent subsequence. In the
yeah,
quasi-regular work, when one has to invoke some kind of higher integrability and some careful LP estimates. So that's in some sense the hardest step, right?
yeah, yeah, absolutely.
But the yeah, it's funny. I mean, the basic ideas are very, very similar.
Yeah. Um, all right. So, um, in the last few minutes, let me now give some evidence that these things are not equivalent um, just by explaining that they're completely inequivalent for open manifolds. So even for surfaces, or even for metrics on R2, they're not equivalent. Um, right. So um, here, quasi-regular ellipticity is equivalent to um, their to being conformally equivalent to the Euclidean plane, right, versus the hyperbolic plane, which are the two options for what you're conformally equivalent to, it turns out. Um, and uh, so this is well studied or fairly well studied. And so um, it turns out to be possible to construct uh, both elliptic metrics that are conformally equivalent to the hyperbolic plane and non-elliptic metrics that are conformally equivalent to R2. So let me just give the examples. Um, so this example is somewhat complicated. Basically, what you do is you take R2 and you make a grid on it, and at every in every grid square you make a spike, and um, these spikes should be height about log of the radius, so the distance from the origin. And so it turns out that um, there's this estimate, or there's this computation for um, whether a metric on R2 is parabolic or elliptic. It's from the 30s. I forget who it's due to, someone famous. I should remember this. But you basically have to integrate the radii of geodesic balls, or sorry, of geodesic spheres. Sorry, you have to integrate the circumferences of geodesic spheres. There, it came out right that time. Um, and if it's bigger than a certain amount, you get um, hyperbolicity. But yeah, it turns out that this is not elliptic. And then If you want something conformally equivalent to um, uh, to H2, but it is elliptic, you just have to um, take a radially symmetric metric with curvature 1 over r squared at radius r. So somehow, it's sorry, I wrote down 1 over r squared. I probably meant minus 1 over r squared. So somehow it's negative enough to make this thing hyperbolic, but the stuff grows slowly enough to make it elliptic. Okay, that's really confusing terminology. Um, and then in higher dimensions, things get even wilder. First of all, for any um, open manifold, there's an elliptic metric versus for quasi-regular ellipticity, there are actual obstructions. And the way you build it is you take some geodesic that goes to infinity, and you unzip at this geodesic, and you glue in just a copy of Euclidean space, which is unzipped at on, say, the positive x-axis, and then you can um, you can construct a wrapping map that just hits this half plane and completely ignores the rest of the manifold. Um, and okay, so you might say, well, this is kind of stupid. This manifold suddenly has infinite volume. So what if can you do a finite volume thing? And yes, you can. So if you have a manifold um, that just has a puncture somewhere, then you can glue on this sort of funky spire with um, with shrinking nodules with even more shrinking necks between them. Um, and the fact that this doesn't have a Cheeger constant turns out to again, you can make a wrapping map that only hits this spire and ignores everything else. So then you might ask, okay, well, what if the manifold has a Cheeger constant? And then you can get an actual obstruction, which is similar to an obstruction to quasi-regular ellipticity, which is for quasi-regular ellipticity, um, uh, this obstruction actually extends to open manifolds. And for ellipticity, it extends to open manifolds with a Cheeger constant. Um, but even with those restrictions, there are still examples of things that are elliptic, but not quasi-regularly elliptic. For example, you take an n-sphere and you remove some countable number of points from the equator. All right, so that's my story. Thank you very much for the invitation.
Yeah, thanks a lot. Yeah, let me open the discussion. Are there comments or questions? So if I understand right what you said at the end here, there's no Picard theorem for these elliptic maps. I mean, for, let's say, spheres, standard spheres with points removed.
Yeah, so you can, yeah, there's no Picard theorem. You can come up with an elliptic map from Rn to Sn minus a codimension 2
Ah,
sphere.
I see.
Yeah, so that's actually the map that we come up with, and then right the example that's not quasi-regularly elliptic with any metric is um, if you put back most of the points of that equatorial sphere except for a countable number.
Other comments or questions?
So I guess I'm not sure if this is something you know know how to answer, but I'll ask just out of curiosity. Have you thought about these same sort of ellipticity questions with other manifolds down there than Rn?
Um,
Like one that I'm curious about is Rk cross Sn minus k. Uh, that inherits most of the restrictions that these should have on the quasi-regular side because you have the covering map from Rn to Rk cross Sn minus k. But do you win anything more in that case?
I haven't thought about that particular version at all. I've thought about a little bit about the version where um, the um, the origin manifold is a or is a nilpotent Lie group, and I actually have a student working on that question, and it may be related to some recent results of Gioacchino Antonelli and Robert Young.
Right. Okay. So that case is still because I was curious that if there are any results there that might give a guess what to sort of expect in the quasi-regular case. Because what I know about it is really weird so far. Like
Interesting. Yeah, I'd love to
odd
talk more about it.
the odd case is the fact that it doesn't feel like it feels like you should have stronger limitations on the cohomology for like S2 cross Rn minus 2 or S3 cross Rn minus 3 or something like that. But then suddenly when you hit Sn cross R, then that's conformally equivalent to a subset of a Rn, which Pekka Pankka pointed out to me way back in like 2019, and that suddenly means that you can also map that to a n-torus, so you are not getting any stronger cohomological limitations. So that's what feels really weird to me about that case, and I was curious
Hmm.
if that similar situation happens on the Lipschitz side also. Because the
Um,
conformal embedding in that case, that might not be Lipschitz. That might I don't think that's globally one Lipschitz.
yeah, I don't think it is. So that may be another situation where there are different phenomena.